Okay, so just a little bit on this worksheet to follow up from the lab, and so you can do problems 1 and 2. And then, the rest of them pretty much going to have you take a look at the solutions. All right, so again, from the lab, this is pretty much what we learned, Newton's second law. You can read these notes, acceleration equals F net over mass, or the way we use it very often is F net equals ma. So the more mass something has, the less it accelerates at a given force. All right, so the acceleration is dependent upon the force and the mass, but bigger mass, less acceleration, bigger force, more acceleration. So this first example is a pretty good one to look at. 400 newtons pulling this way, 350 newtons pulling that way, right? That's probably, since it's to the left, it's probably actually should be a negative 350. So the net force in this case is 50 newtons, positive 50. 350 cancels out from that 400, we're left with positive 50 newtons of force, which on a 60 kilogram object would give us 0.83 meters per second. Now, if this was a 120 kilogram object, the acceleration would be half of that. All right, it'd be a lot less. So the problems here, solve each problem, include a force diagram. All right, 2200 kilogram sports car can accelerate at a rate of 30 meters per second squared. Which types of forces must be acting to determine the strength of the overall net force on the car. All right, so what individual forces are acting? Well, we're going to have, as always, Fg and Fn. All right, then there's some sort of force propelling this. It's actually the force of the road on the tires, because believe it or not, when you imagine that's the road, right? Here's the bottom of the tire. All right, so as the tire turns, it rotates, right? And it pushes against the road. Well, it's that friction there, static friction, in fact, that actually propels the car forward. It's kind of an interesting thing. Anyway, so then against that force of the road, you have maybe the force of the air or drag, something like that. But it doesn't even matter individually what those forces are. The net result of those ends up being the mass times the acceleration. Just gotta pause it real. All right. So F net equals ma. The mass here. Mass is F net is 2,200 kilograms times the acceleration of 30 meters per second squared. That's going to be 66,000 newtons, F net. So overall, this has to be 66,000 newtons. If you know the mass and acceleration, you can get the total for force. All right, a block on a frictionless table accelerates at a rate of 5 meters per second squared when a 30 newton force is applied to it. What must the mass of the block be? So again, we're going to have Fn, we're going to have Fg, we're going to have the applied force. But this time, we're not going to factor in air drag or anything like that. We're just going to go ahead. So the force, this is that 30 newtons. All right, so F net equals ma. We're going to solve for mass though, so we're going to divide both sides by a. We're going to get mass equals F net, force applied divided by the resulting acceleration. All right, so the net force, 30 newtons, acceleration, 5 meters per second squared. It's going to give me 6.0 kilograms. Now, the units here are interesting to look at. Newtons per kilogram, right? Well, Newton is a kilogram times a meter per second squared. Oops, sorry, Newton per meter per second squared. So what happens is meters per second squared, and you're left with kilograms. That's how we got the unit there. All right, there's another one. 2 kilogram block. Frictionless table, another one. All right, it's going to have Fg and Fn. Most of the time we don't need to use the y direction here. We just need to worry about the x direction typically, or the direction it's accelerating in. The block starts from rest. All right, starts from rest. That means the initial is 0. All right, that's the time. We're looking for V final. So So this looks like a motion problem, right? Yeah, I'm going to be looking for the final velocity. So if you look at your equation sheet, you see v final equals v initial plus acceleration times time. Well, I know the time, I know v initial, I don't know the acceleration, but I do know the mass and the force, right? So that's mass and that's force. So we'll use Newton's second law, A equals F net over m, 6 newtons divided by 2 kilograms. That gives me an acceleration of 3 meters per second squared. And then, if I know it accelerates at 3 meters per second squared, put it in over there, so I get v final equals v initial, that's 0, plus acceleration, 3 meters per second squared, times the time, 2 seconds. One of the seconds cancels. You get v final equals 6 meters per second. Very good. All right, number 4 here. Magnus for Magnusson, world famous strongman, had to pull with a force of 1,500 newtons, so we're pulling with 1,500 newtons. All right, to accelerate a small 1,100 kilogram car at a rate of 0.4 meters per second, so mass acceleration. Now, what is that force? That is Magnus's force. All right, this is F Magnus. Now, if I do F net equals ma here, I get 1,100 kilograms times 0.4 meters per second squared. That gives me 440 newtons of net force. So if Magnus is applying 15,000 newtons, there's some sort of force resisting it. It's taking away most of the force. This is Fn and Fg, they just cancel each other out. So this resistive force, all right, I should put that on there. This resistive force is smaller than the 1,500 newtons because we know it's accelerating. So I'm going to introduce this little arrow. When I draw this arrow, it's to represent the direction of the acceleration of the object. All right, so this object's accelerating to the right here. So the 1,500 newtons has to be 440 newtons bigger than whatever's resisting. All right, so when we do this calculation, that's telling us, you know, the total sum of the forces, considering the signs as well, all right? So this is, it's actually that 440 newtons, that's what the force of Magnus plus the drag or resisted must add up to. So if Magnus is 15,000 newtons, right? And it's got, and that 15,000 is 440 bigger than the resist. The resist must be 14,560 newtons. And it's going to be negative, right? Well, it's got to be negative. So that brings you up to speed with class. We did talk a little bit about what's going on in 5 and 6. All right, just to get you set up. 7's kind of difficult. Don't remember if I talked about it in class with the students a bit. But anyway, pulled in opposite directions by 10 Newton and 8 Newton force. So opposing directions. All right. Let's say that's the 10 Newton, that's the 8 Newton. All right. What will its acceleration be? Well, for this one, F net equals ma, or A equals F net over m. What's F net? Is it 18? Is it 2? What is it? Well, technically it's actually 2 because this 8 newtons pulling to the left. So net force, remember, it's the sum of the forces, including if they're negative. So F net is actually positive 2 newtons the way I drew it, divided by 5 kilograms. All right, so 0.40 meters per second squared. Now, if these are pulling in the same direction, the 8 and the 10 are in the same direction, that would be a net force of 18 newtons. Right? So if they're both pulling to the right, it it'd be a net force of positive 18, both pulling to the left, it'd be net force of negative 18. If we switched it and the 10 was pulling to the left and the 8 to the right, then the net force would be negative 2. So you got to be careful when you draw these things. Now this one I'm not going to do fully right now. I want you to try to figure it out. This is the mass. Mass equals 0.04 kilograms. This is a distance, an 8-meter long barrel, so it's how far it's going to travel at a speed of 300 meters per second. That's V final. The initial would have to be 0. It's, shot out of a barrel. With what average force was it propelled? So that's basically F net. So we're going to have to find the acceleration first. All right. Probably using something called the V squared equation. Find the acceleration first. Then you know the mass. You can figure out what the force must be. It's pretty darn big. It's the overall force, right? 2 ropes at a right angle from the top view. All right, so that means they're going like this. We're looking down at above. It's a sled, right? So here's the sled. People are pulling it through heavy snow. So there's a whole bunch of friction. Gravity and normal force are actually going up and down relative to this view. This is a top view. So that's important to think about. Each one of these is pulling at 300 newtons. 300 newtons. All right? And this sled is accelerating that way at 0.8 meters per second squared. Determine the force of friction acting on the sled. All right, so F net equals ma. All right, so 60 kilograms times 0.8 meters per second squared. 6 times 8 is 48, so that's 48 newtons is what the net force has to be. So that means the forward force has to be 48 newtons bigger than the backwards force. Now, how do I figure out the forward force? Well, you got to find the components of the 300. All right, this one has 2 components, right? They both have 2 components. These 2 components cancel each other out, right? They oppose each other and cancel each other out. These 2 components add together and go together. So let me just recap this, so I just realized this was a little bit off the screen. So from the top view, the sled looks like this. It's got 2 ropes pulling at, basically, this is going to be 45 degrees right here and 45 degrees right here. All right, 2 ropes pulling at an angle. Their x components cancel each other out. Their y components add together to go against friction. And so you got to figure out this component, which is 300 times the cos of 45. All right, and you have 2 of those because this one and this one going together. So you're going to have whatever that is. You're going to have 2 of those. All right, 2 times 300 cos of 45 minus the force of friction, because the force of friction is going against them, must equal 48 newtons. So now this is kind of an interesting thing. Let's call this FT1 and FT2. Let's call these the y components. All right, so FT1y plus FT2y minus the force of friction must equal 48 newtons, because the friction is resisting those 2. So that's what we got here. These are each 300 cosine, 300 cosine. See if you can figure that one out the rest of the way. All right, and refer to the solution. That's a hard question. That one's more like AP level, but maybe you can figure it out. All right, so let's get you up to problem 7, roughly. Good luck.